Exotic matter uncovered in the Sun's atmosphere. Scientists from Ireland and France have announced a major new finding about how matter behaves in the extreme conditions of the Sun's atmosphere. The scientists used large radio telescopes and ultraviolet cameras on a NASA spacecraft to better understand the exotic but poorly understood fourth state of matter. Known as plasma, this matter could hold the key to developing safe, clean and efficient nuclear energy generators on Earth. The scientists published their findings in the leading international journal Nature Communications. Most of the matter we encounter in our everyday lives comes in the form of solid, liquid or gas, but the majority of the universe is composed of plasma, a highly unstable and electrically charged fluid. The Sun is also made up of this plasma. Despite being the most common form of matter in the universe, plasma remains a mystery, mainly due to its scarcity in natural conditions on Earth, which makes it difficult to study. Special laboratories on Earth recreate the extreme conditions of space for this purpose, but the Sun represents an all-natural laboratory to study how plasma behaves in conditions that are often too extreme for the manually constructed Earth-based laboratories. Postdoctoral researcher at Trinity College Dublin and the Dublin Institute of Advanced Studies, DIAS, Dr. Owen Carley, led the international collaboration. He said, "The solar atmosphere is a hotbed of extreme activity, with plasma temperatures in excess of 1 million degrees Celsius and particles that travel close to light speed. The light speed particles shine bright at radio wavelengths, so we're able to monitor exactly how plasmas behave with large radio telescopes. We worked closely with scientists at the Paris Observatory and performed observations of the Sun with a large radio telescope located in Nankai in central France. We combined the radio observations with ultraviolet cameras on NASA's space-based Solar Dynamics Observatory spacecraft to show that plasma on the Sun can often emit radio light that pulses like a lighthouse. We have known about this activity for decades, but our use of space and ground-based equipment allowed us to image the radio pulses for the first time and see exactly how plasmas become unstable in the solar atmosphere. Studying the behavior of plasmas on the Sun allows for a comparison of how they behave on Earth, where much effort is now underway to build magnetic confinement fusion reactors. These are nuclear energy generators that are much safer, cleaner and more efficient than their fission reactor cousins that we currently use for energy today. Professor at DIAS and collaborator on the project, Peter Gallagher, said, "Nuclear fusion is a different type of nuclear energy generation that fuses plasma atoms together, as opposed to breaking them apart like fission does. Fusion is more stable and safer, and it doesn't require highly radioactive fuel. In fact, much of the waste material from fusion is inert helium. The only problem is that nuclear fusion plasmas are highly unstable. As soon as the plasma starts generating energy, some natural process switches off the reaction. While this switch-off behavior is like an inherent safety switch, fusion reactors cannot form runaway reactions. It also means the plasma is difficult to maintain in a stable state for energy generation. By studying how plasmas become unstable on the Sun, we can learn about how to control them on Earth." The success of this research was made possible by the close ties between researchers at Trinity, DIAS, and their French collaborators. Dr. Nicole Villemur, lead collaborator on the project in Paris, said, "The Paris Observatory has a long history of making radio observations of the Sun, dating back to the 1950s. By teaming up with other radio astronomy groups around Europe, we are able to make groundbreaking discoveries such as this one and continue the success we have in solar radio astronomy in France. It also further strengthens scientific collaboration between France and Ireland, which I hope continues in the future." Dr. Carley previously worked at the Paris Observatory, funded by a fellowship awarded by the Irish Research Council and the European Commission. He continues to work closely with his French colleagues today, and hopes to soon study the same phenomena using both French instruments and newly built, state-of-the-art equipment in Ireland. Dr. Carley added, "The collaboration with French scientists is ongoing and we're already making progress with newly built radio telescopes in Ireland, such as the Irish Low Frequency Array (ILOFAR). ILOFAR can be used to uncover new plasma physics on the Sun in far greater detail than before, teaching us about how matter behaves in both plasmas on the Sun, here on Earth and throughout the universe in general." The work was funded by the Irish Research Council. Formation of the Moon brought water to Earth. The Earth is unique in our solar system. It is the only terrestrial planet with a large amount of water and a relatively large moon, which stabilizes the Earth's axis. Both were essential for Earth to develop life. Planetologists at the University of Munster, Germany, have now been able to show, for the first time, that water came to Earth with the formation of the Moon some 4.4 billion years ago. The Moon was formed when Earth was hit by a body about the size of Mars, also called Theia. Until now, scientists had assumed that Theia originated in the inner solar system near the Earth. However, researchers from Munster can now show that Theia comes from the outer solar system, and it delivered large quantities of water to Earth. The results are published in the current issue of Nature Astronomy. From the outer into the inner solar system. The Earth formed in the dry, inner solar system, and so it is somewhat surprising that there is water on Earth. To understand why this is the case, we have to go back in time when the solar system was formed about 4.5 billion years ago. From earlier studies, we know that the solar system became structured such that the dry materials were separated from the wet materials. The so-called carbonaceous meteorites, which are relatively rich in water, come from the outer solar system, whereas the drier, non-carbonaceous meteorites come from the inner solar system. While previous studies have shown that carbonaceous materials were likely responsible for delivering the water to Earth, it was unknown when and how this carbonaceous material, and thus the water, came to Earth. We have used molybdenum isotopes to answer this question. The molybdenum isotopes allow us to clearly distinguish carbonaceous and non-carbonaceous material, and as such represent a genetic fingerprint of material from the outer and inner solar system, explains Dr. Jarrett Buddy of the Institute of Planetology in Munster and lead author of the study. The measurements made by the researchers from Munster show that the molybdenum isotopic composition of the Earth lies between those of the carbonaceous and non-carbonaceous meteorites, demonstrating that some of Earth's molybdenum originated in the outer solar system. In this context, the chemical properties of molybdenum play a key role because, as it is an iron-loving element, most of the Earth's molybdenum is located in the core. The molybdenum, which is accessible today in the Earth's mantle, therefore, originates from the late stages of Earth's formation, while the molybdenum from earlier phases is entirely in the core, explains Dr. Christoph Burkhardt, second author of the study. The scientists' results therefore show, for the first time, that carbonaceous material from the outer solar system arrived on Earth late. But the scientists are going one step further. They show that most of the molybdenum in Earth's mantle was supplied by the protoplanet Theia, whose collision with Earth 4.4 billion years ago led to the formation of the Moon. However, since a large part of the molybdenum in Earth's mantle originates from the outer solar system, this means that Theia itself also originated from the outer solar system. According to the scientists, the collision provided sufficient carbonaceous material to account for the entire amount of water on Earth. Our approach is unique because, for the first time, it allows us to associate the origin of water on Earth with the formation of the Moon. To put it simply, without the Moon there probably would be no life on Earth, says Thorsten Kleine, professor of planetology at the University of Munster. Unexpected observation of ice at low temperature, high pressure questions water theory through an experiment designed to create a super cold state of water. Scientists at the Department of Energy's Oak Ridge National Laboratory used neutron scattering to discover a pathway to the unexpected formation of dense, crystalline phases of ice thought to exist beyond Earth's limits. Observation of these particular crystalline ice phases, known as ICE-X, ICE-15 and ICE-8, challenges accepted theories about supercooled water and amorphous, or non-crystalline, ice. The researchers' findings, reported in the journal Nature, will also lead to better basic understanding of ice and its various phases found on other planets and moons and elsewhere in space. Hydrogen and oxygen are among the most abundant elements in the universe, and the simplest molecular compound of the two, H2O, is common, said Chris Tolk, ORNL neutron scattering scientist and lead author. In fact, a popular theory suggests that most of Earth's water was brought here through collisions with icy comets. On Earth, when water molecules reach 0 degrees Celsius, they enter a lower energy state and settle onto a hexagonal crystalline lattice. This frozen form is denoted as ice-IH, the most common phase of water that can be found in household freezers or at skating rinks. Ice X, Ice 15 and Ice 8 are 3 of at least 17 ice phases realized when molecules reorganize into a stable crystalline structure at varying super low temperatures and very high pressures, conditions that don't occur naturally on Earth. As ice changes phases, it's similar to water going from a gas to a liquid to a solid, except at low temperatures and high pressure, the ice transforms between various different solid forms. Tulk said. Each known ice phase is characterized by its unique crystal structure within its pressure-temperature range of stability, where the molecules reach equilibrium and the water molecules exhibit a regular three-dimensional pattern, and the structure becomes stable. Initially, Tulk and colleagues at the National Research Council of Canada and from the University of California at Los Angeles were exploring the structural nature of amorphous ice, a state of ice that forms with no ordered crystalline structure, as it recrystallizes at even higher pressures. To make amorphous ice, scientists freeze water into a high-pressure device that is cooled to -173 degrees Celsius and pressurized to approximately 10,000 atmospheres, or 147,000 pounds per square inch. Car tires are inflated to about 32 pounds per square inch. This type of amorphous ice is thought to be related to liquid water, and understanding that link was the original purpose of this study, said Tulk. At ORNL's spallation neutron source, the team froze a 3 mm sphere, or about half a drop, of deuterated water, which has an additional neutron in the hydrogen nucleus needed for neutron scattering analysis. Then, they programmed the spallation neutrons and pressure, or SNAP, diffractometer to -173 degrees C. The instrument increased the pressure incrementally every couple of hours up to 411,000 pounds per square inch, or about 28,000 atmospheres, while collecting neutron scattering data between each hike in pressure. Once we achieved amorphous ice, we planned to raise the temperature and pressure and observe the local molecular ordering as the amorphous ice melts into a supercooled liquid and then recrystallizes. Tulk said. However, after analyzing the data, they were surprised to learn they had not created amorphous ice, but rather a sequence of crystalline transformations through 4 phases of ice with ever-increasing density, from ice IH to ice X to ice 15 to ice 13. There was no evidence of amorphous ice at all. I've made many of these samples always by compressing ice at low temperature, said co-author Dennis Klug from the National Research Council of Canada, the lab that originally discovered the pressure-induced amorphization of ice in 1984. I've never previously seen this pressure-temperature path result in a series of crystalline forms like this. If the data from our experiment was true, it would mean that amorphous ice is not related to liquid water but is rather an interrupted transformation between 2 crystalline phases, a major departure from widely accepted theory, Klug added. At first, the team thought their observation was the result of a contaminated sample. 3 more experiments with a fresh, carefully handled samples on SNAP produced identical results, reconfirming the structural transformation sequence with no formation of amorphous ice. The key was the slow rate of pressure increase and collection of data at a lower pressure that allowed the ice structure to relax and become the stable ice X form. Previous experiments quickly passed over the ice X structure without relaxation. This resulted in the amorphous phase. For 35 years, scientists have been researching the properties of super cold water and looking for what's known as the second critical point, which is buried within the solid ice phases. But these results question its very existence. The relationship between pressure-induced amorphous ice and water is now in doubt, and the second critical point may not even exist, Tulk said. The results of this paper will form the basis of the analysis of future studies of amorphous ice phases during upcoming experiments done at the SNS, he added. Co-authors of the study titled, Absence of Amorphous Forms When Ice is Compressed at Low Temperature, included Chris A. Tulk and Jamie J. Malizan of ORNL, Adam McClough and Craig E. Manning of UCLA, and Dennis D. Klug of the NRC of Canada. Experimental measurements were performed at ORNL's spallation neutron source, a DOE Office of Science user facility, using the spallation neutrons and pressure diffractometer. The research was supported by DOE's Office of Science and the Sloan Foundation's Deep Carbon Observatory, a global community of more than 1,000 scientists working to better understand the quantities, movements, forms and origins of carbon inside the Earth. Scientists break record for highest temperature superconductor. University of Chicago scientists are part of an international research team that has discovered superconductivity, the ability to conduct electricity perfectly, at the highest temperatures ever recorded. Using advanced technology at UChicago-affiliated Argonne National Laboratory, the team studied a class of materials in which they observed superconductivity at temperatures of about -23 degrees Celsius (-9 degrees Fahrenheit), a jump of about 50 degrees compared to the previous confirmed record. Though the superconductivity happened under extremely high pressure, the result still represents a big step toward creating superconductivity at room temperature, the ultimate goal for scientists to be able to use this phenomenon for advanced technologies. The results were published May 23 in the journal Nature. Vitaly Prokopenko, a research professor at the University of Chicago, and Eran Greenberg, a postdoctoral scholar at the University of Chicago, are co-authors of the research. Just as a copper wire conducts electricity better than a rubber tube, certain kinds of materials are better at becoming superconductive, a state defined by two main properties: the material offers zero resistance to electrical current and cannot be penetrated by magnetic fields. The potential uses for this are as vast as they are exciting: electrical wires without diminishing currents, extremely fast supercomputers, and efficient magnetic levitation trains. But scientists have previously only been able to create superconducting materials when they are cooled to extremely cold temperatures, initially, -240 degrees Celsius and more recently about -73 degrees Celsius. Since such cooling is expensive, it has limited their applications in the world at large. Recent theoretical predictions have shown that a new class of materials of superconducting hydrides could pave the way for higher temperature superconductivity. Researchers at the Max Planck Institute for Chemistry in Germany teamed up with University of Chicago researchers to create one of these materials, called lanthanum superhydrides, test its superconductivity, and determine its structure and composition. The only catch was that the material needed to be placed under extremely high pressure, between 150 and 170 gigapascals, more than 1.5 million times the pressure at sea level. Only under these high-pressure conditions did the material, a tiny sample only a few microns across, exhibit superconductivity at the new record temperature. In fact, the material showed 3 of the 4 characteristics needed to prove superconductivity: it dropped its electrical resistance, decreased its critical temperature under an external magnetic field, and showed a temperature change when some elements were replaced with different isotopes. The 4th characteristic, called the Meissner effect, in which the material expels any magnetic field, was not detected. That's because the material is so small that this effect could not be observed, researchers said. They used the Advanced Photon Source at Argonne National Laboratory, which provides ultra-bright, high-energy X-ray beams that have enabled breakthroughs in everything from better batteries to understanding the Earth's deep interior, to analyze the material. In the experiment, researchers within University of Chicago's Center for Advanced Radiation Sources squeezed a tiny sample of the material between 2 tiny diamonds to exert the pressure needed, then used the beamline's X-rays to probe its structure and composition. Because the temperatures used to conduct the experiment is within the normal range of many places in the world, that makes the ultimate goal of room temperature, or at least 0 degrees Celsius, seem within reach. The team is already continuing to collaborate to find new materials that can create superconductivity under more reasonable conditions. Our next goal is to reduce the pressure needed to synthesize samples, to bring the critical temperature closer to ambient, and perhaps even create samples that could be synthesized at high pressures, but still superconduct at normal pressures. Prokopenko said. We are continuing to search for new and interesting compounds that will bring us new, and often unexpected, discoveries.